The next example will show the effect of a slew rate on the linearity performance of an amplifier. For this example, we have exactly the same circuit as before with slight modifications. So now this amplifier that has been connected as a voltage buffer will be driving a load of 10 picofarads. Amplifier itself, it contains a compensation capacitor of 2 picofarads, and the biasing current for this circuit is 10 microamps, and so 10 microamps will enter in M7, and then this current mirror will feed with the biasing current to the differential pair and to the common source output. So the current that it is coming to the differential pair is 5 microamps, and the current that it is going towards the output stage, the common source stage, is 30 microamps. Okay, so we're going to run different simulations on this circuit. So let's see. When we run an AC simulation on the circuit as it is right now, we will see that the bandwidth that I have after an AC simulation, let's take a look. We put a marker here. So let's see, this is 0 dBs and minus 3 dBs somewhere around here. So the bandwidth of this circuit, it is around 6 megahertz. Okay, is just above 6 megahertz, which looks extremely good. But we have to be extremely careful when we see these kind of numbers, because remember that the AC simulation is taken with linearized models, with a linearized circuit, so it doesn't tell us absolutely anything about the linearity of the circuit. So we really have to test if we in fact can put signals at very high frequencies, and that if linearity requirements are going to be accomplished. So let's simulate every let's run a simulation for only 1 kilohertz. We're going to run only 1 kilohertz simulation with a signal swing of 500 millivolts at the input. So we run this simulation, and we run this simulation, and then we see our output, sinusoidal signal with an amplitude of 500 millivolts that we expected. And then we just take a look how it looks in frequency. So we go take the spectrum, we check this signal, that it is a 1 kilohertz signal, is very low frequency, so we expect very good linearity performance at very low frequencies, normally dominated by static nonlinearity. And then we take a look for fundamental. We put a marker on the second order distortion, and then let's create a delta marker to see the distortion level. So we created delta marker, and then we have that the distortion that we have at low frequencies is the D2, the second order distortion is minus 58 dBs. We move the marker to the third order distortion, and then we see that this one it is very low, 90 dBs, so very close to the noise floor. So maybe we cannot really trust this number. But anyway, the message here is that we have really good distortion performance at 1 kilohertz. Now, as we checked before, the bandwidth of this circuit is above 6 megahertz. So yeah, we can, for instance, try to see what happened with a signal of 3 megahertz, same amplitude, 500 millivolts amplitude. So let's run this simulation and take a look. And then we have something totally different. Okay, so let's send it to a new window. Then there are several things that have happened here, and to start with the amplitude, it is totally different. It is not anymore 500 millivolt amplitude, and the other thing is that there is really a strong distortion in this signal. It has been distorted. It is not a sinusoidal signal anymore. It looks more like a triangular wave, and then we don't even need to check the distortion levels. The signal is totally distorted, and many things might happen in a real application. If the information is, for instance, in the amplitude and in the phase, then we will have a very strong deterioration on the quality of the recovery of the information signal. If it is a system that needs to be bandwidth limited, the harmonics will be located at much higher frequencies and probably causing interference in other systems. So this is a serious problem. And what is the cause of this problem? If we now simulate a step, we're going to put a step at the input, a very strong step, also 500 millivolts step. We're going to check what happened at the output. So this is a very sharp step. Actually, we can put here a label and then get it simulated as well. Okay, so we put them here and then let's add a signal. We can add it here, much easier. Output to be plot, select on design. And we select it here. So it is already there. This one I will just delete it. And then we close it and then we send it to simulation. So we're going to pass a very large step at the input. And then let's take a look at the simulation result. Okay, so let's send these two output signals to another window. And then we can see something very interesting here. This is the input signal, this is the output. So we have a very sharp step at the input. The output cannot follow very quick. So if I zoom it, then we can see that the signal, it is just changing slowly over time, and then it is just converging at the final voltage. That is what it is expected. But this slope that we see here is what we call the slew rate. The slew rate of the system, and it is basically limiting the speed at which my signal can change at the output, and it has very strong implications on the maximum amplitude and frequency that I can drive at the output of my amplifier. And then I can actually measure this one, and here in simulation what I do is I am using an equation here to calculate the slew rate, that in this particular case is around 2 megavolts per second. So I can just sample it, the output at a particular time, subtract it, and then just divided by the delta time, and then I got this slope, the slope that it is in volts per second. Okay, so what happens here? So we have our amplifier here. We have our amplifier here, and then at the output we have put our load. Put our load at the output, and then the signal, it is slowing, as we saw here. The output signal. The output signal, it is basically slowing like this at a particular slope. Okay, it has a particular slope here. If we take mathematically this, we assume that we have let's see. We make it very, very big here. If we have a sinusoidal signal, very slow like this, we'll go like this, and the maximum slope that my signal can tolerate, it is just m. Then the problem happens with these slopes here, that are the largest slope at the sinusoidal will happen here, will happen here, will happen exactly at zero crossings. That is where we have the maximum slope. So we have to calculate that this slope, it is never exceeding the maximum slew rate or slope that my amplifier can tolerate. And for that one, then we have the output voltage V out, assuming that we have a signal of amplitude Vm. If this is the amplitude Vm. This will be Vm sine and that will be 2p ft, and then we just derivate this one, dv out divided dt, and then that will be 2p f bm, and then cosine of 2p ft. And then the maximum happens when the cosine is equal to 1, and that is at as I mentioned before, here are the zero crossings at 0 and pi and 2 pi. So this term will become 1 at those phases, at those times. And then we have that the maximal slope we can define with the following expression. Okay, and then here we this will be limited by the amplifier, so we can either find which is the maximal frequency that I can tolerate for a particular voltage of the output, or the other of what is the maximum voltage that I can tolerate at a particular frequency. So this is a voltage and frequency combination, the ones that need to be considered, not only one or the other. They are coming both hand by hand. So let's calculate for our example here the maximum frequency, so that I can tolerate. That will be equal to the slew rate of my amplifier divided by 2p and Vm here. In my particular case, I have that the Vm is 0.5 volts, 500 millivolts that I am entering this amplifier, and then we have that the slew rate. Okay, and for the slew rate, as I mentioned before, I just measure it, and then it was around 2 megavolts per second. And then yeah, we can calculate this F max. This F max, when we plug in these numbers, is equal to 636 kilohertz. Okay, so we have F max approximately 600 kilohertz. So this is actually the maximum frequency that I can put in this amplifier before it slew it, the output, the output entering is slewing. Okay, so let's go back to our circuit and let's take a look if that is true. So where is here? It is our circuit. So now we are going back here to this one, and then we are change this 3 megahertz. Okay, we're going to change this 3 megahertz to, let's say, we're not going to put 600 because it's just too close, but let's put 500, so half a megahertz, and then let's run the simulation. Okay, we're going to close this one, and then now we are back. Our signal it is much more linear, as we see here. We can take this signal and send it to the spectrum and check the distortion levels. We plot it, and now we can see the distortion is dominated by weak distortion. So we are basically back with a linear amplification. Okay, so let's take very quickly the distortion levels here. Create a delta marker, and then we see that the second order distortion, it is around 45 dBs under the fundamental, which is clearly that now the distortions are dominated by weak distortions, and it is not as good as at 1 kilohertz, and that is totally normal. Remember that in the loop gain, this amplifier is a physical system. There are always more poles than zeros, so the loop gain will decrease at higher frequencies and eventually will reach zero, and then there will not be loop gain. So the higher the frequency, the lower the loop gain, and then we can naturally understand that the correction of the nonlinearities will not be as effective as at low frequencies. But now this is working at 500 kilohertz. Yeah. Now, what is the origin of this slowing rate? So if we go back to our circuit here, we can create a new page here, and then we take a look to our circuit, and then we can just draw it very quickly. The first stage. So we had here our differential pair, and our current mirror here. Our current mirror looks like this. And our amplifier, common source amplifier, look like this. The load is here. So we have 10 picos, and then we have this compensation circuit located here, and this is here. And this is connected here. So we have our amplifier here, and then the input it is here. And let's see the current levels where we have 5 microamp for the differential pair and 30 microamp for the output. So here we have 5 microamp and here 30 microamp. And the capacitor, it is 2 picofarad, the compensation cap. So we have 2 picofarad here and 10 picofarad here at the output, and then this is the output. And this is Bin. Okay, now what is the problem here? Now think, if I put a very sharp step here, okay, if I put this very sharp step here, this transistor is basically going to become a switch. Okay, it is going to become like a resistance is going to really become like a very low resistance, and on the other side the other transistor will open, because all the current, all these 5 microamp current are going to be channeled in this direction like this. Okay, so this other transistor here will starve and then just become like open circuit. So all this current is going to be channeled like this. The current mirror will stop working completely, because there is no current flowing in this transistor either. So all these 5 microamp will be channeled directly to the capacitor, and they are going to flow in this direction. Okay, and then the maximum speed in which this capacitor it is charged will basically is easy to calculate. So we have the capacitor is equal to delta Q divided by delta V. And then we have that delta V it is equal to delta Q divided by C. We change this to delta V equal to delta Q divided by C, and then we just divide these ones by time. Delta Q, delta time, and then 1 divided by C. Then we have that the slew rate at the capacitor is equal to the current divided by the capacitor itself. So this is very important equation, because in this particular case we have only 5 microamps available to charge this capacitor. Let's see what happens if instead of having a positive step we have a negative step. We have a negative step, then it is the transistor on the left, the one that will get starved. It will just switch off, and all the current will pass through this transistor. It will go to the current mirror, it will be mirrored, and then it will come like this. In this case it will flow in this direction. So this capacitor will charge at the same speed, charge and discharge at the same speed depending on this current. So we can say at this capacitor will charge, we put this the compensation capacitor, and I think which number it is. This is capacitor 3 here on the top. This capacitor 3 and this capacitor 1. Let's try to keep these values. This is C3 and this is C1. So the slew rate in C3 it is going to be equal to 5 microamp divided by 2 picofarad, and the slew rate in C1 it is going to be equal, and we see what happened in C1. C1 there is this current, it is the, let's change the color, this current source, that this one it is the one that it is going to be limiting the discharge rate of capacitor 1. We think This one, it is not really going to, I mean, this common source transistor will be able to provide currents, charging current depending on the how it are the voltages and currents in the previous state. But the real limiting factor here is 30 microamp. It is totally limited the amount of current that it is available to discharge this capacitance. So in this direction we have 30 microamp available to discharge. Then for this here the capacitor one, then we will have around 30 microamp divided by 10 pico in the best case. In practice, there are other considerations. For instance, I might have the situation in which this current, that it is 5 microamps, it is also drained by the current source at the output. So if we do Kirchhoff current law over this node, what we have it is something very interesting. So we will have that these 5 microamps entering here, 5 microamp, 5 microamp, 30 microamp going down. Then actually I will not have all this 30 microamp flowing here. I will just have 25 to discharge this capacitor. So there are also these kind of situations that appear that are affecting the slew rate of the amplifier. So what I did is that I have a very simple script that just give a rough estimation of the slew rates for each capacitor. So when we run this script, we have that for the capacitor C3 we have a slew rate of 2.5 megavolts per second, and for capacitor 1 we have 3. Okay, so this is the slowing without assuming that we have these currents are adding and subtracting at the node. Now these are more or less already an indication of the performance that I should expect. So it will be below 2.5 megavolts per second, that it is my limiting. So when I run a step simulation in Cadence, I run the simulation, and then we will just run the slew rate. Okay, this is predicting me around 2.1 mega, so that it is a little bit lower than what I have for capacitor 3. But remember that there are the other capacitors around that are also involved, and then this let's say situation in which both capacitors have been charged and discharged. So we have to assume that the situation is going to be slightly worse than for the individual capacitance. So in this case I got it very quickly. It was around 2 megavolts per second, and then as we did it before, we calculated the maximum frequency around 600 kilohertz. For if we need higher performance, and I mean we will need to do something about it, and then we will need to just increase the current now to be able to charge and discharge this capacitor faster. Let's say that we need in our application higher performance, like 1 megahertz, not 500 kilohertz, 1 megahertz. Then we will have to increase the current in which these capacitors are charged and discharged. And one way of doing that, it is basically changing the current mirrors or changing the biasing current of the whole amplifier. So now I'm going to just double the biasing current, so we will have 10 microamps for the differential pair and 60 microamps driving the output. So in principle that will double the slew rate of my amplifier. Yeah, I can play a little bit of how much current comes to the input and the output, but for now we are just going to double the biasing current here. And then I will first, let's take a look to the slew rate simulation to see how much it has improved. Now we have 4.5 megavolt per second, which is much better. And we go back to our equation here. So we had that the slew rate we calculated it was equal to 2p f max times the amplitude. Then we have the maximum frequency. In this particular case is around 4.5 megahertz divided by 2p 0.5, and this is equal to, let's calculate it very quickly. So we have 4.5 this is 1.4 megahertz. 1.4 megahertz. Okay. So let's take a look. If we double this from 500 meg, so we can just take a look to the slew rate very quickly to see how it has improved. And we see that slew rate is a little bit faster than before. So we're not going to simulate at high frequency. We go to variables and then we double the frequency to 1 meg, and then we send it to simulation, and let's see. Okay, so then what we have here, it is again a much more linear system, more linear curve. We're going to check the spectrum of this signal. We send into the spectrum, and then to a new window we plot, and then yeah, we can take a look at immediately this. The distortion here, it is dominated by the weak distortion. So we get the marker, create a delta marker, and then around 43 decibel, minus 43 decibel the D2, the distortion of second order, and 47 the distortion of third order. So that is how we get a better frequency performance and not slowing. Our limit was at 1.4 megahertz. So let's take a look what happened at 1.4 megahertz just for curiosity. We sent this simulation, and then okay, so then let's take a look. The distortion levels, measurement, spectrum. window plot. Okay, then we can see that it is deteriorating already the harmonic distortion. So we have around 30 dBs under the third order, and the second order also it is around 30 dBs. So it is starting to become very strong distortion. Despite that, the transient that we can see it start getting distorted the signal. So we cannot really work very close to the limit. So we can see that the sinusoidal is getting distorted. Okay. This was the second example. So the last thing as a summary, we have that the last stage is normally the main source of distortion in an amplifier, and the bias of the last stage is the one that should be able to handle the load and the feedback under maximum signal condition, that it is at the higher frequency of operation and the maximum amplitude. So they are the both things that are important, as we saw in the last example. So we have to provide enough bias, both voltage and current, to avoid clipping distortion, but also to avoid slowing the amplifier. The loop gain corrects for weak nonlinearities, as we saw before. As long as there is enough loop gain, the differential error will be minimized or will be attenuated. At higher frequencies, unfortunately, the loop gain will drop. It is unavoidable. So we expect to have stronger linearity at higher frequencies. The use of the common source stage, it is recommended at the output whenever possible. It is naturally possible to use common drain and common gate stages, but the common source stage is the best from the linearity point of view. Other stages should not be used. Impedances on series or shunt should not be used. And the last thing is that the balance stage are very useful because they cancel even order distortion.